there is an aircraft capable of crossing half the planet, entering the most heavily protected airspace in the world without being seen, and striking a target with surgical precision. This is the B-2 Spirit, the greatest stealth bomber ever built in the world. But everyone already knows that, and that is not the most interesting part. What really makes this bomber incredible happens before it ever leaves the ground, because behind every B-2 Spirit mission, there is a secret army behind the preparation. There are thousands of steps, and nothing can go wrong there wrong. Because when you are operating an aircraft that costs $2 billion and carries massive bombs, any tiny mistake, and this aircraft can turn into the most expensive mistake in the world. And to understand why it is considered the most powerful military aircraft ever built, today we are going to show every secret behind one of the most incredible aircraft in the United States military today. From preparation to striking a real target. And then you will understand why it is one of the most powerful weapons in the world. The preparation does not begin with the aircraft. It begins inside the 59th Munitions Squadron of the United States Air Force. That is where specialized crews prepare the weapons that can be loaded into the internal weapons bay of the B-2 Spirit. These personnel will install a kit on standard gravity bombs that will turn them into extremely precise guided bombs. This kit is called the JDAM, or Joint Direct Attack Munition. And the entire assembly goes through a process that removes any margin for error. Throughout the entire building, air, humidity, and temperature are tightly controlled. That happens because the guidance systems are sensitive to dust and moisture. The temperature stays fixed at 20 degrees Celsius. And it is not for the crew's comfort. This happens because inside these guidance systems there are laser gyroscopes that can lose accuracy if the temperature changes by only a few degrees. The first step of the assembly is attaching the MAU-169 guidance system to the front end of the weapon. That is the point where the bomb starts becoming a smart weapon. Inside that assembly there is a small GPS antenna about the size of a human palm. Right below it sits an inertial measurement unit with accelerometers so sensitive they can detect tiny movements even in something as thin as a strand of silk. These sensors work with a control module that receives target data sent by the aircraft and turns that information into commands for the bomb's correction fins. But there is an even more important component in this process: the umbilical connector. It is what allows the B-2 to communicate with the weapon system inside the weapons bay. Without that connection, the weapon loses its guidance capability and becomes an extremely expensive object, completely useless. That is why technicians use specific torque wrenches to secure the guidance system. If the torque is below spec, vibration can cause a failure. If it is too tight, the structure can crack. After that, they install the tail guidance kit, where the movable fins and actuators are located, the components that give the bomb precise control. And those fins are not simple metal surfaces. Each one is controlled independently by extremely precise electric motors, capable of correcting position by 1/10 of a degree. And before any bomb leaves that building, the actuators are tested with programmed movements. Because if one of those fins jams for just half a second, the bomb can miss the target by more than 30 meters. Then comes another critical stage, the weighing process. The finished weapon is weighed with precision because the B-2 mission computer depends on that exact value to calculate the ballistic trajectory. A difference of just over 2 kilograms is already enough to change the release point. Even with all this sophistication, one rule does not change. The bomb must remain safe. The fuse remains unpowered, and the guidance system remains in test mode, so there is no risk of detonation. The thermal battery that powers the fuse only becomes active after experiencing the extreme forces of ejection in flight. Until it is released by the B-2, it is still not a bomb. It is still just an inert body, highly sophisticated. When inspection of the bomb systems is finished, it is cleared and moved to transport trailers. But the weapons still are not loaded. Before that, the bomber has to prove it is ready to receive them. On the bombs, the focus was mechanical perfection. On the B-2, the focus shifts to electromagnetic performance, and that has to be measured by technicians with millimeter precision. On the flight line, technicians from the 393rd Bomb Squadron face the greatest enemy of this aircraft's stealth. That is physics. The B-2's invisibility to air defense systems is the result of an extremely careful control of how the aircraft interacts with electromagnetic energy. And that only works if the surface of the aircraft is practically flawless before any bomb is loaded into the bay, even before a single drop goes into the aircraft's tanks. The B-2 must go through a stage that determines whether it will truly remain invisible or not. Because in this airplane, stealth is not an extra feature, it is the very condition that allows the mission to exist. The B-2's outer coating does not work like the paint on a normal aircraft. There is a special layer designed to manage radar waves. Part of that energy is dissipated as heat by a material containing microscopic metallic particles in its composition. In practice, that helps prevent the radar signal from returning with enough strength to reveal the aircraft's position. The problem is that this material is relatively fragile. A bird strike, or even very heavy rain, can compromise that outer layer. And any unevenness in that skin can change the way radar reflects and possibly reveal its location. That is why the inspection is nearly obsessive. The entire fuselage is analyzed millimeter by millimeter. Technicians look for the smallest imperfections, rough patches, tiny bubbles, uneven spots, and any mark capable of scattering electromagnetic energy in the wrong direction. The leading edges receive priority because they are the first surfaces hit by radar waves. The engine air intakes are also on the list of the most important areas. If there is any irregularity there, it can create what they call a radar reflector, like a beacon that gives away the aircraft's position. The joints between panels go through the same strict standards. Every seam must remain smooth, uniform, and with no visible contour. A tiny gap between parts, even as thin as a sheet of paper, is already enough for radar to detect the aircraft, and defects show up all the time. When that happens, the repair starts with precision sanding. It is an extremely complex procedure. If the team sands too much, it creates radar reflection, but if they sand too little, the repair compound will not bond properly. Then comes the absorbent material used in the repair. It has a very short application window of just a few minutes. Any mistake can create a radar reflection point. When the surface hardens, the leveling process begins. The finish requires special tools to remove tiny fractions of material, almost impossible to notice with the naked eye. In the end, the allowed variation across every 30 centimeters of surface has to be only a few millimeters, smaller than the thickness of a few sheets of paper stacked together. And because of this complexity, B-2 maintenance takes so much time. The crews are not just servicing the aircraft, they are making sure one of the most incredible weapons ever built by the United States is truly effective and completely invisible. While this team works like true artists, another group, the mechanics, examines everything to guarantee the aircraft is fully operational. The hydraulic system, for example, operates under pressures so extreme that they can slice through steel. The B-2 uses 4 independent circuits to guarantee redundancy. If 1 or 2 fail, okay, the mission continues. If 3 fail, the aircraft can still return, land safely, and be replaced by another one. The actuators that move the control surfaces are checked for any abnormality. Because this aircraft has no tail, every single control component is extremely important. Brakes, tires, landing gear, the environmental systems that keep the pilots from freezing at altitude, the electrical buses that connect everything, radios, navigation equipment, and even the bomb release mechanisms. Everything goes through inspection, and there is one non-negotiable rule. If any system fails, weapons loading stops immediately. The B-2 cannot receive a single bomb before proving that it is technically flawless. Only after that approval are the weapons brought to the aircraft. The bombs are positioned beneath the bomber and placed on hydraulic lifts. They will be raised into the internal weapons bay. That is essential because the B-2 cannot carry munitions externally. All the weapons have to remain inside the fuselage for stealth to work. The doors of this bay are enormous. Each one weighs approximately as much as a large car, and even the alignment of the hinges matters. Any geometric deviation there can create radar reflection. Inside is one of the most interesting and ingenious mechanisms on the aircraft: the rotary launcher. It works like a giant revolver cylinder with 8 positions, each one capable of holding a bomb weighing about 900 kilograms. The entire assembly rotates 360 degrees in less than 3 seconds, moving nearly 8 tons of explosives inside the aircraft while airborne. The bombs are secured on suspension hooks designed to support around 6.3 tons each. That may sound excessive, but it is not. During combat, in a 2G maneuver, the effective load doubles. Add turbulence and structural movement, and each bomb can effectively weigh 2 tons. The fit between the aircraft and the bomb also has to be exact. Just a few millimeters out of place are enough to compromise electrical power or data transfer. The teams lock the attachment points and connect the cables responsible for communication between the bomb and the B-2 Spirit weapons management system. That connection is critical. Without it, the bomb does not receive target data and reverts to a standard gravity bomb, and could miss the target by miles. Even so, the coordinates are still not loaded into the bomb at that moment. On the ground, it still does not know where it is going. That data stays in the aircraft's mission computer until shortly before release, and that creates 2 advantages: safety and flexibility. If the situation changes during flight, the target can be changed in real time. Even with everything installed, the bomb remains inert. The fuses stay deactivated, and only the minimum test and communication functions remain available. The logic is simple. The less active the weapon is before the right moment, the safer the entire process becomes. When the airplane is already loaded, the team's attention shifts completely. Now, it is time to guarantee the safety of the people who will fly this machine all the way to the target. In the flight equipment section of the 59th Operations Support Squadron, specialists inspect everything that keeps the crew alive at extreme altitude. The B-2 flies above 15,000 meters. That is so high that a loss of cabin pressure would be fatal without oxygen. That is why the pilots need pressurized suits and special masks. The masks go through test benches that simulate breathing at high altitude. They must continue delivering oxygen even when the pilot is under extreme G-force. Because under those conditions, breathing is like trying to pull in air with an 80-kilogram weight pressing down on your chest. Communication cannot fail either. That is why the microphone is tested with the same level of rigor. In a real emergency, there is no time to fix audio and communication problems. The helmet is also not just physical protection. It integrates head-up display functions, compatibility with night vision, and shielding against extreme flashes, including the brightness of a nuclear detonation. The visor can go from transparent to opaque in milliseconds, faster than the human brain processes the pain caused by an intense flash. And the cost of just one helmet like this can exceed the price of a large house. The survival vest is also inspected. It has an emergency beacon, signal mirror, reflective strips, and even water purification tablets. Everything designed for the real possibility of ejection over hostile territory. The anti-G suit is also very important and is individually fitted and given special attention. Its inflatable bladders have to maintain the exact pressure. Pressure too low and the pilot can lose consciousness during maneuvers. Pressure too high and the suit itself starts interfering with breathing. This suit is custom-made and precisely adjusted for each person. And in an aircraft capable of carrying out missions lasting up to 40 hours with aerial refueling in flight. The comfort of the suit and the pilot's cockpit is not just a luxury. It is an operational requirement to make the mission possible perfectly. With the aircraft ready, the weapons installed, and the crew equipped, one of the riskiest stages of the entire ground routine of the United States Air Force arrives. Refueling with the engines running. In most airplanes, refueling with engines on is completely normal. But in the B-2 Spirit, it is not that simple. the B-2 is refueled with all 4 engines at idle. That avoids the long shutdown and restart cycle. But the risk rises sharply. Each engine produces enough heat to melt aluminum in seconds. That is why the teams approach with great caution, and there are strict emergency procedures in case something gets out of control. They also carry extinguishers capable of projecting suppression foam about 9 meters away. The entire procedure is carefully calculated. The first step is grounding the aircraft. During flight, it builds up static electricity. There are thousands of volts stored there, looking for a way out. Without grounding, one touch and a single spark near fuel vapors would be enough to cause a catastrophic explosion. That is why a thick cable, close to 5 centimeters in diameter, is attached to a specific point on the landing gear where bare metal is exposed. Only after that are the high-flow hoses connected to the fueling system. The fuel is flowing at approximately 600 gallons per minute. In less than 30 minutes, the aircraft can receive about 75.7 tons of JP8, which is the fuel used by the US in aircraft like this. But refueling a B-2 does not mean just filling tanks. Weight distribution has to be precise. Too much weight in front makes the aircraft nose heavy. Too much weight in back compromises stability. And in this aircraft that looks like a tailless flying wing, mass balancing is extremely important. Fuel temperature also enters the equation. Too cold and it does not circulate properly through the engines. Too hot and vapor bubbles can appear, capable of causing an engine failure. That is why pressure, flow, and temperature are monitored the entire time. The noise is enormous and makes any conversation impossible. So communication is done by hand signals and headsets. When this stage ends, the bomber is fueled, armed, verified to preserve its stealth, and ready to receive the crew. The pilots enter through a hatch located behind the nose landing gear and climb a ladder to the cockpit. There they find the seats. And these are not ordinary seats. They are ejection seats that cost more than a luxury sports car. They are complete survival systems capable of launching the crew out of the aircraft in less than 1 second. And even in extreme situations, if the B-2 is inverted or very close to the ground, it can still remain fully effective. After settling in, the pilots connect the oxygen lines, switch on the intercom, and begin the startup sequence. The B-2 cockpit is fully digital. Screens, keyboards, electronic systems. Nothing in the setup is analog. The B-2 computers has enormous processing power. The mission computer alone surpasses the processing power of everything that was used in NASA's Apollo program to reach the moon in its time. But no technology will help if the startup sequence fails. The inertial navigation units then begin their alignment. This process takes about 8 minutes. During that period, the aircraft cannot move even 1 centimeter. The laser gyros are measuring the Earth's rotation to define their own reference. If there is any interruption, everything starts again from zero. Then, the military GPS comes in. Unlike conventional GPS devices, this one is far more secure and precise, with an error margin of only a few meters. During taxi, the pilots check the control surfaces. The B-2 does not have a conventional rudder, and it also has no vertical surfaces. Directional control is done by drag rudders on the wingtips that open like air brakes to help turn the aircraft in the desired direction. If that system fails, maintaining coordinated flight becomes a serious problem. These combined flight control surfaces are called elevons. They travel through their full range, move up, move down, and act differentially to control roll. Before takeoff, the crew reviews rotation speed, abort criteria, and emergency procedures for possible engine failure. Loaded with maximum weight, the B-2 uses a large portion of the runway to get airborne. The margin for error is minimal, so the throttles advance. All 4 engines come out of idle and rise to maximum power. That is about 31 tons of total thrust, pushing an aircraft weighing more than 152 tons. The nose wheel leaves the ground first, then the wing finally produces enough lift to lift clear of the runway. At altitude, thin air reduces the engine's available thrust to a fraction of what they deliver at sea level. The B-2 continues on autopilot, but that does not mean it stays stable by itself. The onboard computers have to make constant corrections, around 1,000 adjustments per second in order to keep a tailless aircraft stable. Without those computers, flight would not be possible. When the target gets close, the crew begins the verification procedure for all the weapons. It defines which bomb will be released first. Inside the weapons bay, the rotary launcher begins to turn and positions the selected bomb for launch. The bay doors remain closed until the last possible moment. Opening too early would mean increasing reflection to enemy radars from a very long distance. Then, the moment arrives. The doors open only for the time necessary to release the bomb. Nothing beyond that. The sudden change in airflow shakes the aircraft, and the computers react in that same second to compensate and correct the course. It is only at that instant that the bomb becomes fully active. Through the umbilical connector, the B-2 mission computer transmits a flood of data to the bomb system. All the data the bomb needs to reach the target is passed. Precise GPS coordinates, wind speed and direction at various altitudes, barometric pressure, estimated time to impact, and the planned angle of attack. The bomb's internal guided system computer processes all of that in milliseconds and runs a self-diagnostic. It confirms fin operation, checks GPS, and establishes a link with the satellites. It validates inertial navigation. It prepares the battery for activation. All of this happens in milliseconds. Almost in the blink of an eye, everything is already configured. The actual release lasts fractions of a second. The hooks open, the pneumatic ejectors activate. The bomb is pushed out at about 1.2 meters per second. Fast enough to clear the bay, but not enough to maintain initial stability. At the exact moment the umbilical connector breaks away, the entire logic of the weapon changes. The thermal battery ignites and reaches operating temperature almost instantly. The fuse starts its arming sequence and confirms the required G-forces. The GPS receiver begins to connect to the satellites, 4, 6, and 8. It locks onto as many satellites as possible. The greater the number of satellites, the greater the accuracy. Inside the guided bomb, the computer calculates everything at an impressive speed. It knows where it is, it knows where the target is, and it calculates the best trajectory to connect those 2 points. But that trajectory is not straight, it is a complex curve, because it takes into account the wind, air density, and even the Earth's rotation. After release, the system makes the necessary corrections. It could be a slight bank to compensate for a crosswind detected by the B-2 sensors. A guided bomb does not fly like a self-propelled missile. It uses gravity but turns the fall into a precision-guided descent. Every small movement of the fins gradually leads the bomb to the target. If the GPS is damaged, inertial navigation takes over with lower precision, but the weapon keeps working with an accuracy of about 30 meters instead of 10. During descent, the adjustments become smaller and more frequent. In the final 10 seconds, the fins can correct the trajectory hundreds of times. In the final moments, the radar altimeter comes online to report the exact height over the target. The computer calculates the exact moment of impact. Then comes the final correction, a minimal adjustment, almost imperceptible, made fractions of a second before impact. And that is what separates a common bomb from a weapon capable of striking exactly where it was planned. Then it strikes the target with extreme precision.